resume. So, Azure SQL Data Warehouse in the context of the Cortana Intelligence Suite. Firstly, the Cortana Intelligence Suite is a platform and the process to perform advanced analytics from start to finish. So when you talk about the Cortana Intelligence Suite, you'll probably think about the marketing slide that we have with a plethora of technologies, and it can seem quite overwhelming. Well, here in the analytics and data science team, we also think about the process a lot as much as we think about the technologies. But between the team data science process and the Cortana Intelligence Suite, we're going to enable you to fulfill the platform and the process of advanced analytics from beginning to end. So from a process perspective, we do talk about the team data science process. This starts off with getting a business understanding where you're defining the business objectives. Here you may be identifying data sources. Fundamentally, you're trying to refine the questions that you're actually trying to answer. And once you get through that phase, then you've got the data acquisition and understanding. And this is where you'll use technologies to ingest data, explore data, you might update information about that data itself, and fundamentally you'll want to find places to store it. Modeling deals with the feature selection. Features in this context, it could be a column from a table, it could be an attribute from a cube, it might be a variable within our data set. We're going to wrap these up into the term feature. Essentially, features is data that is of interest to a machine learning model. So fundamentally, there's two really important parts. You've got the model itself that deals with the algorithm, and then you've got the features, which is the data going in. And from this, we create and train the model, we score it, we evaluate it, and if all is well, we can go to deployment and operationalize it. Finally, we've got customer acceptance, where we've got testing and validation. Sometimes the validation may yield results where you have to go back to the process. Maybe the model wasn't right, so you go to modeling and change the algorithm. Maybe the features that you selected were overfitted, so basically it provided a bias in the results, so you might want to change the features, in which case you may go back to the data acquisition phase. The key thing with the team data science process is that it's an iterative process until you get that customer acceptance and handoff. And even then, once that's been accepted, you may come back and review it down the line through retraining and rescoring newer data sets against the models that you have. So we have a platform that can accommodate this process through the Cortana Intelligence platform. A good friend and colleague of mine, Buck Woody, has done a video about an overview of the Cortana Intelligence Suite. I do encourage you to watch that 15-20 minute video. What we're focusing on in the Cortana Intelligence Suite today is SQL Data Warehouse. So this is the first of a series of videos that are going to explore many different aspects of SQL Data Warehouse, but in this video today we're looking at the key concepts that you need to get your head around. So in the context of the marketing slide, the previous slide may have looked like a raft of technologies and oh my god, that's overwhelming. I would ask you to stop and consider this. If you're a SQL Server professional, do you truly know all the technologies in SQL Server as an expert? Reporting services, analysis services, integration services, the database engine, replication, full text search, the full T-SQL language, not forgetting all the other languages across the board ranging from XMLA or DMX or MDX or so forth. I could go on. The reality is that there's very few people who are true experts of the full SQL Server stack, and it's going to be the same with the Cortana Intelligence Suite. You may specialize in an area of the Cortana Intelligence Suite and become a real expert in that area, but essentially be aware of the other areas. So rather than be overwhelmed, I break it down into these four parts. On the left hand side, we deal with information management. So we've got Data Factory for the batch movement of time-based data. We've got event hubs that deals with the ingestion of real-time data. So here we can deal with time slicing in real time. And then we've got Data Catalog that deals with the documentation, tagging, of your data sources or data stores. So it doesn't have to be a source, it could be a destination. It could even be an intermediate storage area like an Azure Blob Store. So with information management, you're dealing with that ingestion of data and documentation of data. But at some point you're going to have to store that data somewhere, and this is where we move on to the second phase, which is big data stores. So a lot of people in the BI space will be familiar with a data warehouse, and what these series of videos will do will help you become very familiar with Azure SQL Data Warehouse. So this deals with relational structured data stores. And with Data Lake Store, here we're dealing with unstructured data stores as well. So if you're a BI professional or a SQL Server professional or even a business analytics professional, you know, the first two phases of the Cortana Intelligence Suite, information management, big data stores, this deals with what we call in the world of data science features engineering, where you're ingesting that data, you're preparing it, you may do some transformations, you're storing it for downstream analytics purposes. So if you feel that a world of data science is beyond you, it's not, because there's a space in there called features engineering, where a lot of the skills that you have already in the SQL Server space can be easily transferred to information management and big data stores. That's not to say you don't have to learn anything. You do have to learn some new things, but I think the transition into the world of data science will be made much easier by entry points here. But we move on to the analytics phase, where we've got the hot topic machine learning, where you're doing the modeling and retraining models and he's scoring and evaluating them. We've got data lake analytics that sits over a data lake store using USQL to perform analytics. We've got HD Insight, which is our implementation of the Apache Hadoop standards. You've got to bear in mind with HD Insight, as much as it's a base storage layer with Hadoop, there are also different flavors of HD Insight that you can have, such as Spark, Storm, HBase. These deals with very specific areas, so Spark allows you to do analytics over huge volumes of data. Storm allows you to do real-time processing of huge volumes of data, and HBase provides NoSQL solutions. And then we've got streaming analytics that's closely tied into event hubs. So with the streaming data coming through an event hub, it's typically sent to streaming analytics to do what we call complex event processing, but we've made this easier by integrating it with a very familiar T-SQL language. The final phase is what I like to call consumption. This is subdivided into two areas, visualizations and intelligence. So the visualization, we've got Power BI, which enables you to create your dashboards and reports. Cortana can actually hook into Power BI through the data set, so you can use Q&A through Cortana against Power BI. And then we've got the bot framework to provide interaction points and cognitive services for a raft of APIs that we provide to provide a wide range of detection and so forth in various industries. Today we're going to focus on SQL Data Warehouse, and in this series of videos we break Azure SQL Data Warehouse into a number of different component parts. So what is Azure SQL Data Warehouse? Well, it's a database, data warehouse as a service. Fundamentally, it takes full advantage of the Azure capabilities that's provided by us here at Microsoft. It's the first elastic cloud data warehouse, and we've got enterprise grade capability, but it can handle small loads right through to massive data storage up to petabyte level, and it can handle queries up to 100 times faster through a combination of technologies that we have under the hood to do it. So what we get is elastic scale and performance. We can scale to petabytes of data. This is done through what we call massively parallel processing. We have the ability to scale the data warehouse in terms of its compute size in seconds, and we can query both relational and non-relational data. And this is all powered by the cloud, which not only has all the inherent benefits of Azure as a managed service, but also its tight integration with other technologies in the Cortana Intelligence Suite, such as machine learning, Power BI, and ADF. And because we've worked with enterprises for decades, a lot of the capabilities that we have are enterprise ready. We've got a simple billing and compute model. A key point of Azure SQL Data Warehouse is that we can pause the compute. That means we only basically start it when we need it, so therefore we only pay for it when we need it. So you've got really interesting scenarios here. Firstly, from a scaling perspective, you might scale to a high level during a full data load, and once that data load is complete, let's say for example if that completed at 3:30 in the morning, you might scale back, but then you might pause it and restart it again at 7 a.m. in the morning. You're not paying for the compute aspect between 3:30 to 7 because you've paused it. So fundamentally, there's a lot of capabilities there that you can get right out of the box, and these capabilities you're actually going to see in this session today. So what is massively parallel processing? Well, it's the notion of a divide and conquer strategy. If you work with data warehouses on premise, you've probably got a server somewhere, and it's got the memory configured to a certain level and CPUs and disk storage, and they've probably been configured to the maximum capacity that you planned out your data warehouse will be. Well, these are typical of symmetrical multiple processing systems. So, you know, when you start to hit performance problems there, you know, some people will start to ask, well, do we have enough memory? Or, well, memory's cheap, let's buy some more. Or do we need more CPUs? Do we need to increase the disk storage? So fundamentally, regardless of that, you're still on the same service bus, the same motherboard in order to do that. With massive parallel processing, you're basically taking multiples of those servers and then taking one big problem like a big query where it's broken down into little queries, and each little query is executed individually on each of those servers, so to speak. So MPP is very much a team approach of many hands make light work. And under the hood, what it requires is really a method of scheduling those tasks between all the available servers, if you will, that partake in massive parallel processing. There needs to be a communication plan between all that to maximise the transfer of the queries and the data coming back, and a distribution method for the exchange of that data as well. And we'll take a look at that as we go through this slide deck. So the logical overview of Azure SQL Data Warehouse is that at a high level it's broken down into two layers. Firstly, you've got the storage layer, which is provided by Premium Azure Blob Storage. And secondly, we've got the compute layer, which are many finely tuned SQL servers under the hood that's partaking in the work involved. Now, as I mentioned earlier, the key benefit to Azure SQL Data Warehouse is the ability to scale the compute. And we can literally scale up in seconds. So, as I say, if you're doing a data load overnight, you might scale up for the purpose of that data load. And when the data load finishes, you then scale back to a level where the queries can be handled appropriately. You can pause it as well, which effectively means that the compute layer is not there. So you're not paying for that compute layer. Don't get me wrong, you'll pay for the storage layer, but in comparison to the compute, that's really cheap. And when you want to resume operations and access that data, you start the compute up again. So how do distributed queries work? Well, essentially within the compute node, we've basically got two levels of servers in there. We've got a control node. Now the control node is responsible for accepting the requests and breaking down that big query, if you will, into manageable chunks. Basically within the control node there's an empty shell DB that holds metadata about the configuration of the Azure SQL Data Warehouse. From there it knows which control nodes are dealing with which data, so that when a request comes through, it's able to break that big query, if you will, down into smaller queries and pass it on to the appropriate area. The compute nodes will basically take those smaller requests from the control node, build up in what's called a massive parallel processing execution plan, and then push that down to be executed against the storage nodes. So fundamentally, when a query comes in, the control node will divide that work up across all the available compute nodes, which then pushes it down for processing in the storage node. And then essentially what happens when each individual result is returned back to the compute nodes, the control node will probably perform a final aggregation of all those individual queries before sending the result back. So from a high level perspective, it's very straightforward. Just think of it as two-level compute and storage, but the compute level we have a lot of control over from the scalability and the ability to pause and resume. There is geo-redundancy built into these solutions if you so wish. Effectively, what that means is that the storage is basically, there's a geo-redundant copy of that storage. If anything should happen on your primary Azure SQL Data Warehouse, you can fire up another compute across the redundant data that you have. Now, the key point of massive parallel processing is parallel loads. Now, we're looking at the architecture we've just seen on previous slides, but on a sideways view. So on the left-hand side, we've got the control node. And in the middle, we've got the compute nodes. In this case, we've got 3 nodes. So all of these have something called a data movement service. And fundamentally, the control node, as we know, will pass down the smaller queries down to the compute nodes. What the compute nodes will then do is issue the queries and get the storage to process those queries. And what we need really is full parallelism between each of the nodes across each of the Azure storage blob. Now, this just doesn't happen automatically, and one of the things that you'll learn in a later session is that your choice of loading tool is absolutely critical. So fundamentally, there are occasions where you can't take advantage of that parallel load simply because you're using the wrong tool for the job. But bear that in mind at the moment. Keep it at the back of your mind for, I would say, video 3 of this. It is a fully managed platform as a service. Here we've got a screen dump of what it looks like in the portal, but I will give you a demonstration of that. There's a wide range of connectivity options for Azure SQL Data Warehouse for Windows or Linux through ODBC, OLADBC, OLADB, JDBC, ADO.NET and PHP as well. Let's talk about what you should use this for and what you shouldn't use this for. So the target workloads for Azure SQL Data Warehouse are analytical workloads. It's geared up to store large volumes of data. It will deal with small volumes as well. This is why we have the elastic scale of Azure SQL Data Warehouse. Look, the notion of data warehousing is no different to what it was 10 years ago. It is about consolidating disparate data from various sources into a single location. At that point within there, you can shape, model, transform and aggregate the data. Azure SQL Data Warehouse is geared up to perform query analysis or ad hoc reporting across huge volumes of data. And all this is done using simple SQL constructs. It's like a SQL on SQL. What I mean by that is a lot of the code that you'll see will be T-SQL, but you'll see some variations of that SQL. So maybe there's additional code that's needed for create table statements. When you're using partitioning in Azure SQL Data Warehouse, you don't have to create the function, for example, in order to do it, because the T-SQL required to do partition is far simpler. But by and large, you're going to be very comfortable if you use T-SQL with what we've run here as well. If you have a scenario where you need high throughput with high concurrency, transactional consistency of the data is hugely important. There's a large number of singleton selects, then Azure SQL Data Warehouse is not the tool, the service to use. Those attributes I just talked about are very common for OLTP, online transactional processing environments. SQL database is geared up exactly for that scenario. So, you know, high concurrency, high transactional consistency, think SQL database. If you've got data that's perhaps in a JSON format, it's going to be more appropriate to think about document DB instead. For other data types that are relatively unstructured, semi-structured, you'll want to consider data lake. So, you know, just as important as what scenarios to use Azure SQL Data Warehouse, it's also as important to understand when you shouldn't use it, and hopefully that's cleared that up. So let's create an Azure SQL Data Warehouse instance. So what I'm going to do is I'm going to log on to the portal. So we're in the portal. We can actually create an instance of Azure SQL Data Warehouse here. So I'm going to click on New. This will bring up the services blade, which will list the category of services that we have. You can actually type in the first few characters of it and it'll come up, but I know it's in databases and it's also in, it's here as Azure SQL Data Warehouse. So we're going to click on Azure SQL Data Warehouse. This is the provisioning blade, as I like to call it. I like to give blades different names. There's nothing formal in that. It's just the way I've come to get used to it. So first of all, we'll define a database name called AdventureWorks DW. The green tick that you see there confirms that that name is valid. We then assign it to a subscription so we know what it's being charged against, and then we can store it in a resource group. Now, a resource group is a logical holder of services and Azure objects, and what this gives you the ability to do is manage it and maybe view the billing of a particular resource group against that. Now, in my case, what I'm going to do, I'm going to create new, and I'm going to create one called CTORG. It does support underscores in this case. The source database, there's one of three choices that we've got. We can either start off with a blank database, which will take the AdventureWorks DW there. We can choose a sample database, which is AdventureWorks DW, or we can restore a backup. Now we're going to choose sample, and the sample is only AdventureWorks DW here. You can give it a different name if you want up here. And then we're going to store this database in the instantiation of a server object. Now, the way to do that is I can use an existing server that we have, or alternatively, I can create a new server. And in here, I've got to type in the server name, define a server login, define a password, and then choose the location. In this case, we'll leave it as North Europe. There's a really important setting here that says allow Azure services to access this server. So if you've got other services in Azure, that tick will give those other services access to the data warehouse without you needing to configure firewall rules. So what we'll do is we've configured those options. We'll click select. That will then create the server called CTO SQL DW. This is stored in North Europe. Because I've picked a sample database here, I'm unable to change the collation, which is the language settings for the database. If I had selected blank, then I'd be able to specify the collation that I require. And finally at the bottom we've got performance. Now this is where you do your scaling. So at the moment it's set to 400 data warehouse units of DWUs. Now that equals $5.56 an hour. I can either scale down or I can scale up to 6,000, and that's 83.47. The great thing is though is that we can scale up and down at will. Now what I do is click on create. This will take a couple of minutes. So what I'm going to do is minimize this, because another way that you can actually provision an instance of an Azure SQL Data Warehouse server is by using PowerShell. So what I'm going to do here is I'm going to open up PowerShell itself, and I am going to open up a script, and this script is called create Azure DW server. First of all, I've got a variable here called $subscription ID with the subscription ID that I have. What I then do is use add Azure RM account. So the way PowerShell works is kind of a verb noun approach. So it's like add, get, create, and then hyphen whatever the object is. So that's the noun. So from that, we set the Azure RM context using the subscription ID parameter and passing in the subscription ID variable. So it's relatively straightforward, and you do get used to it pretty quickly. Below here is the code for creating a resource group. So I've got two variables of resource group name and RG location. So the resource group name is CTO ADS Prep RG and North Europe, and then I'm using the commandlet, as they call them in PowerShell, new Azure RM resource group. We've got a parameter of name using the variable resource group name, location, RG location, and that's basically how it works. So when it comes to create the server, I've got a number of variables here for server name, version, location, server admin, password. Within variables, I can make use of other commandlets, and in this case I'm using the convert to secure string to protect the server password, and then I've got another variable here for new objects and so forth. Basically the work is done in this final variable SQLDB server, where I'm calling the new Azure RM SQL server commandlet and passing in the variable values for resource group name, server name, location, server version, SQL administrator, credentials. Now there are code for updating the firewall rules. Below here I've got code in PowerShell to create a database. What I'm going to do in this instance is just create the server instance with no database. So in order to do that, I'll run that script. I'm required to authenticate against my instance. So now the authentication has taken place. What you'll see very quickly, it's passing in all that information. It's now logged into my subscription, as you can see there. It's now creating the resource group in North Europe, and that's succeeded. And the resource group is called CTO_ADS_prep_RG. And at the moment, it's going through the creation of the Azure SQL Data Warehouse server instance, and that server instance can then be used to actually provision databases within it. Now this will take approximately a minute. Well, in fact, it just finished. So what we can do now is close the PowerShell script down, go back to our portal, and what we've got here are two very useful areas to look at. We've got all resources, which will show you all the resources within your subscription, and resource groups. So let's go to resource groups first, and what you'll see is I created two resource groups, one during the creation of a data warehouse in the portal and one in the PowerShell script, and there they are, CTO_RG and CTO_ADS.prep. Now what I'm going to do is, if I click on the resource group for CTO_ADS.prep, that will give me information about that resource group, and it will actually tell me the objects that reside, and this could be any object. And there you go, this is the Azure SQL Data Warehouse we created through the PowerShell script. This will then bring up a dashboard and an overview of that Azure SQL Data Warehouse, and what this will confirm when the screen refreshes is that we have no database in there. Correct, so we've got no databases. But the first thing I'm going to do is I'm going to go to the firewall setting here, and within here I'm going to enable other Azure services to access this service, and I'm going to add my client IP address, which means that Visual Studio and Management Studio on my laptop can connect up to this instance. Click on OK. Another way we can look at this is to go to all resources. I've just clicked on all resources there. And basically we have the ability to filter by name. So if I type in CTO, what we get here is the CTO SQL DW. Now this was created in the portal. If you remember, we had the sample database of AdventureWorks, and this should report back one database. So we do have the one database called AdventureWorks. What we're going to do here now is go to the firewall here, and within the firewall you will notice that we've already allowing access to Azure services because we did that as part of the portal. All I need to do is add the client IP address, click on save, and this is typically the first operation you will do once your server is up and running. You will basically set firewall rules to enable access to it. So from this, we'll close the firewall down, and basically we are at the CTO, MSFT, ADS, SQL, SRV instance. Let's go back to the slide. So scaling up versus scaling out. Now, for a lot of your on-prem services, when you're kind of hitting performance problems, you know, after you've finely tuned the system as much as you can, of course, and I always recommend before you spend money, you always follow best practice with regards to tuning your SQL servers. If that doesn't work, then you'll consider scaling up. Now, the reality is with an on-prem server, what you've got is essentially one motherboard, a one bucket, and this is the equivalent of having a glass. And I want to call out thanks to James Rowland Jones and Matt Goswell for inspiring this idea. So think of the motherboard as being a glass, and essentially the resources within the server that are being consumed is like filling it up with water. Well, the thing is, you can chuck loads of straws in it, and this is logical processes that are running within that same box. But the reality of the situation is sometimes, you know, with pressure you only get one straw, so essentially processing things can take a long time. And the reality is that we have customers that are getting to the point where that symmetrical multi-processing model, they'll exhaust the scale-up capability of that, and they need to move on to a new architecture. And this is where scaling out comes in. And essentially, it's the ultimate team game. So rather than having your mates going on a night out for a few drinks and you get a big pitcher or a jug of beer and you get some straws and stick your straws in and bang your heads while you're trying to drink it, what you'll do is all your friends will get their own glass and you'll share that jug of water out. So fundamentally, they've all got their own glass and their own straw. So once, if you have a drinking game and you go, you're going to drink all those glasses a lot quicker than you would do through a full pitcher of beer, for example. So what we've got is that concept is not too dissimilar with massive parallel processing. Rather than having one server doing the work, we have a multitude of finely tuned servers that are basically taking a little bit of the work that needs to be done, working on that little bit of work, and then basically it's coordinated all together as a single result. So the way that we can impact that scale is basically understanding the following keywords: nodes, distributions, and service objectives. Now, when it comes to a node, think of a node as being like a physical server, okay? And then almost think about the distributions as being separate databases. That's the way I think about it. So if you do DW100, you'll always get 60 distributions, they're called, and kind of have this in your mind as being like a database. So you'll always get 60 distributions, it goes without saying. But then if you have one node, all those 60 distributions are stored on that one node. So it's like having 60 databases on a SQL Server instance. But as we scale up, let's say from DW100 to DW200, we can basically split those distributions now across two nodes. So the first 30 might be on node 1 and the second 30 might be on node 2. I think you might get the picture where we're going with this. So a 3 node data warehouse, DW300, is 20, 40, 60. And then of course when we add a fourth, we'll break it down into quarters. And then of course with the fifth node, we're breaking it down into fifths. So essentially, the more you scale up that data warehouse, the more nodes you introduce, the more that those distributions can be distributed across the separate nodes. And that's the way to look at this. Now you can view information about the nodes and the distributions and the data warehouse units. Here we've got a dynamic management view called DMP-DW nodes, where you can identify the node ID, the type and the name of each node within your data warehouse. Here we've got a query that will break against the PDW distributions, which will give you a list of distributions against a particular node with the distribution name and position. And then we've got service objective. Now this is what relates to data warehouse units. Now the data warehouse units and the DWUs is part of that slider that you saw from 100 to 6,000. So why is it called a service objective? Because if you were to use SQL database that has a similar elastic concept through what we call DTUs, database transaction units. So basically, you'll notice in this query at the bottom we've got where addition equals data warehouse, where we are specifically calling out the data warehouse addition to give us the service objective. And the service objective is the generic name for data warehouse units, which could also be transferable to data transaction units within SQL database. So that's why it is. So you can use all these queries that you've just seen to give you information about your nodes, your distributions, and your service objectives. This query will tell you the specific data warehouse units that you are using on a particular node where the type is equal to compute. So this will return back the DWUs that you're utilizing. So what are the scaling options? Well, we can scale in the Azure portal, we can scale in T-SQL, we can scale using PowerShell. So I'll show you how to do it in the Azure portal. Basically, there's been slight changes to the portal compared to this. So essentially, we've got the slider that we can move up and down. Alternatively, we can use T-SQL. So use the alter database statement, define your database name, and then within the modify clause, use the service objective parameter, and then specify DW 100, 200, right up to 6,000. So notice the U is missing. We can do it through PowerShell. So the most important parameter here is at the bottom, requested service objective name. Again, notice it's DW 100. This is using the set Azure RM SQL database commandlet. There are other parameters you need for the resource group, the server name and the database name. But also remember that when you're using PowerShell, you have to log in to your subscription. So the commandlets are here that you need to get access to your subscription. And ultimately using select Azure RM subscription, passing in the subscription name parameter with either a string literal or of course a variable that I showed you in the previous script. So let's show you demo scaling. Now, if I go back into the portal, the first thing to mention is you can only scale at a database level. So at this point in time, with the SQL instance that I created through PowerShell, I've got no database. So I can't scale at a server level. So I'm going to go to the instance that has a database. This will give me the list of databases that I've got. In this case, we created AdventureWorks DW as the sample database. So what I can do here now is go ahead and click on AdventureWorks. This will take up the database blade for AdventureWorks, and you will see a recent change to the portal if you're familiar with this. So what we've now got is, rather than the buttons being at the top here, some of the buttons have moved. So we've now got scale, and this will open up the scale blade, and at the moment we'll get a report of how many data warehouse units that AdventureWorks DW is using. And then what we can do is use the slider to change that data warehouse unit. So in this example, I can scale up. See how it's telling me how many data warehouse units I've used, but I could scale up. Notice how it's purple. Well, that means that change has not been applied. It's blue when the change is applied. So we'll go to DW400 and simply click on save. Notice you get the warning that all executing queries will be stopped. So you'll want to consider doing a graceful exit of queries and transactions before you do this operation. So click on yes. It's now scaling the database. So the database has successfully scaled. So we can close out of that. It's now 400 data warehouse units. And we'll leave it at that point. So moving on, pausing and resume. Another key feature of Azure SQL Data Warehouse is the ability to stop and start the service at will. So the way this works is that if you've got a 5 compute node, you've got the 60 distributions done, you click on pause on that database level, basically the compute aspect disappears, but the storage remains, so you're only paying for the storage. You can pause with the portal. There is a pause button that you can click on, and you can resume in the portal by simply clicking on start. You can also use PowerShell with the suspend Azure RM SQL database commandlet. Basically, you have to specify the parameters of resource group name, server name, and database name. And you can resume with resume Azure RM SQL database name using the same parameters. So let's give you a demonstration of this. What I'm going to do is go back into the portal. Within the portal, click on the AdventureWorks database. This will bring up the AdventureWorks blade again where we previously did the scale, but this time what we'll do is we'll click on pause. And this is done by clicking this button here. We'll click on pause. Are you sure? Click on yes. Bear in mind again, any queries that are issued against the server, any transactions will be disrupted. So again, you need a graceful exit of those transactions and queries. So the pause is completed, and if we were to start it up again, we would just click on the start button. So normally if you were in one of my in-person training, we do a lab on all of this, and I'd ask you to review these questions afterwards. So please feel free to pause the screen if you want to have a look at those questions. As a summary, what we've covered in this session is we now understand that Azure SQL Data Warehouse is a scaled out distributed query engine. It decouples its storage from its compute so we can elastically scale the compute and pause it. It's fully managed as part of Azure. It's completely elastic. It's a platform as a service at petabyte scale. It can integrate and leverage other cloud ecosystem services, and it has a broad range of connectivity options. You can go to learnanalytics.microsoft.com for a list of trainings that are available there, and we have a range of blogs from my good friends Ryan Swanstrom and Buckwoody and myself. Finally, I want to thank you for your time on this session today. I hope it's been very, very useful for you. My name's Chris Test O'Neill, and if you see me on Twitter and that, feel free to ask questions. basis. A lot of this will be familiar to you already. There's a lot of T-SQL syntax slides which they're not designed to blind you with science. They're quite literally there to help you feel more comfortable with doing this and realising that actually with a strong background or even a reasonable background in T-SQL, you should be able to create many of the objects that we see here. There are slight variations that are specific to Azure SQL Data Warehouse, and I'll call them out. So let's have a look at databases first. Basically, when you create a database, you use the create database statement, and it's no different for Azure SQL Data Warehouse. Here we can define the database name, and optionally we can define a collation. There's three options of consideration. Firstly, the max size, which here can be expressed as gigabytes, and there's various sizes there. The edition is important. You need to specify the edition of data warehouse, and the service objective relates back to data warehouse units. We discussed this in part 1 of this series. Now we can also alter the database as well. So from there we can alter the database name by using the modify name. We can modify edition options such as the max size and change the size of the database, or we can modify and change the service objective from one data warehouse unit to another. Now it's really important to mention at this point that when it comes to Azure SQL Data Warehouse, you can't do cross-database queries. So in a scenario in your data warehousing where you may have cross-database queries, maybe in an on-prem scenario, you have to think about a design that accounts for that by using schemas. So a schema is a logical holder of objects, SQL Server objects, and they can be secured as well. But they can also provide a namespace for objects. Now, because we can't do cross-database queries, perhaps when you are bringing in information from different systems, ordinarily a lot of BI professionals would possibly put them in their own landing areas that may be databases and then pull it together into a staging area. Well, perhaps you might want to consider using schemas instead. So you're landing tables in a schema that refers to the name of the data source. So the way we can get around the limitation of not being able to do cross-database queries is actually to place those objects in separate schemas so that all the objects are within the same database, but they are separated by a schema name itself. The code that you use is create schema and define a schema name, no different from on-prem SQL Server. And like on-prem SQL Server, we can define authorization and define a principal that is the owner of that schema, and principals can own other schemas as well. So just bear that in mind. So with the database created, what we're going to do is show you an example of this. Now, in the previous presentation, what we did is we created an instance, a SQL Server instance to host an Azure Data Warehouse database. So what I'm going to do is I am going to log on to the Azure portal. So we're in the portal, and the first thing we're going to do is just go to our resource groups. And in part 1 of these sessions, I created a couple of resource groups. They begin with CTO, and within the CTO IDS Prep RG, I created a SQL Server instance that could host our Azure SQL Data Warehouses. So I'm clicking on that now. And what I'm going to do, time has passed since I recorded the first video. I'm just going to check that my IP address is in the firewall so that I can use various clients to connect up to that particular instance. So if I go to the firewall, what we'll see is the firewall blade appearing, which will give me a list of the IP addresses that are in there. 86184234.168. Perfect, so that's fine. So the other thing to be mindful of as well, is that we want to get the fully qualified domain name of this SQL Server instance, and this will be used to connect up through various client tools. So if I use the properties blade here, what this will do is it will bring up the server name as a fully qualified domain name. So I'll copy that, and what I'm then do is open up Visual Studio. And then I'm going to open up Visual Studio Solution. Okay, so the solution is opened up. It's got a package in there at the moment with an error, but I'm going to show you that in another video. So what we're going to do is essentially make use of what is a create database statement. And as you can see from this create database statement, we have a database called EquityDB. We're setting a collation, and then we're defining an addition as data warehouse, the service objective as DW100, and the max size as 1024 gigabytes. So what we can do is basically, first of all, we'll connect up to the instance, and this is where the fully qualified domain name becomes important. So it's connected up to my local project, so I'm going to change that connection to connect up to the instance of SQL Server that we created earlier. Now, in part one, that was using SQL authentication, where we had an account and a password. And if I click on connect, perfect, you can see at the bottom down here that we have the correct server. Now, this is focused in at the moment in the master database of that instance, so we still have that. So what we can do is highlight this code, and then basically we will execute. And what we've got here is the query that's currently executing. There are a number of dynamic management views that you could actually use to see how that is progressing. So for example, in here I've got create database, and we'll just open up this, and we will connect up So now we're connected to this instance. What we're getting is what is known as the operation status on the actual data warehouse itself. So it's giving us the database name, the operation that it's doing. Now what I'll do is I'll run this now, and in a moment what that will do is it will bring results back saying, hey, we've got a database called EquityDB. It's a create database operation. It's currently in progress. It's telling us what time it started and when it was last modified, and the duration in seconds, and it's looks like it's updating in seconds there. So we can basically get an idea of the status of a database and how it's progressing. Just run it again and it's gone to 60 seconds now, whereas before it was 0 seconds. Again here, if I run this example, it's giving me the name of the server, the addition, and the service objective. But notice we've got a where clause here around data warehouse, so it's just limiting it to that. Let's execute that, and as you can see, this is creating the EquityDB. It's a data warehouse edition with DW100, which is what we created in our initial script. And then one final check of the first query, execute that. Still in progress, 120 seconds. It normally takes about 160 to 180, so that isn't surprising. We can confirm this back here as the query is executing there. So I expect within less than a minute that this should complete itself, but we shall wait for the DMV to tell us. Okay, so the database, EquityDB, completed, and it took 143 seconds. That's great. So what we'll do is minimize Visual Studio, close the instance, go back into it, this will bring up the SQL instance dashboard, where now it should report one database, which is the Equity DB. Great. So that's how we can create a database. Let's move on to tables. And within tables, we're going to cover a number of areas. So firstly, why do we distribute data? So in part one of this series, we talked about the fact that Azure SQL Data Warehouse is indeed a massively parallel processing system. And what that is rather than having your traditional on-prem servers where that's a symmetrical multi-processing system where essentially the memory and the CPU and the disk share the same motherboard, what we have here is different servers that are finely tuned that will divide a big query into little queries, execute them on those various nodes, and then basically they've only got a small part of a bigger query to solve. So this leads to improved performance. So we distribute data to take that divide and conquer approach to improve the performance. And as you would expect, if you're able to evenly spread that data, then that leads to even use of the resources within the Azure SQL Data Warehouse itself. So you need to understand something that's a little bit different with Azure SQL Data Warehouse compared to on-prem SQL servers, and that is referred to as table geometries. So if you're familiar with creating a table structure, essentially you'll use the create table statement, define the columns, names, and the data types, and so forth. Well, here there's a very important clause called distribution, and this determines how the data will be distributed around the various nodes within the Azure SQL Data Warehouse. We have two options. We've got round robin. Round robin will evenly spread the records across all the nodes and all the distributions within an Azure SQL Data Warehouse. So basically what you get here is an even spread, but you don't know exactly which data is on which node. A hash distribution is where the value of a single column will get hash to define a distribution number, which therefore defines in which distribution those records will get inserted based on that hash. So you've got to really think carefully, if you're using hash, what column you should put that on. So for example, putting it on a gender column could lead to uneven distribution. Likewise, if you've got a table with 1 million records and 98% of those records have a city value of Manchester, and you put a hash on that, then that can basically cause uneven distribution. But if you choose a column that's relatively selective, you should basically be able to get a reasonable spread of data across all your available distributions, but also have the situation where the control node of the Azure SQL Data Warehouse is aware of where those values are stored. So it can really help with range queries and so forth. So table geometries are perhaps the most important part that you need to be aware of when it comes to tables in Azure SQL Data Warehouse. So here is an example of a create table statement. Here we've got a table called my table, and we're not worried about the column definitions. The important aspect of this slide is quite frankly the with distribution clause, because what that is defining there is whether or not we use round robin or a hash. Notice with a hash we define a column with it. So do you hash or do you round robin? Well, the guidance for this is you should use hash distribution for factor detail tables if you have a common distribution key which is used in a multi-distribution table join. So if you kind of think about it from a Kimball model with a star schema, and your fact table has a join to your dimension tables, then having a hash on the fact tables and those relevant columns help. The other time to use a hash is if you're getting scenarios where you're getting a full table scan and it's just too slow, because there's because a hash What a hash will do is it will organize the data into distribution so that then when a query comes through, it knows where in the nodes to look. So when should you use round robin? Basically, you should use it when multiple foreign keys are used, like joins. So again, if you think of the star schema, you find that the dimension tables will benefit from round robin. Or another good example is when you do an initial load of data. So you haven't got to the final data warehouse. You might be, if you will, staging data. So what you'll do is you'll just use round robin to do that initial load, so you get an even spread of that data, and then you'll go on to do downstream work to load it into the data warehouse itself. There is something called replication tables, which will be, which isn't a feature in Azure SQL Data Warehouse at the moment. I know that it's on the product group's roadmap. So at the moment, in the absence of that, what you need to do is consider using round robin as well. So you need to remember data movement will most likely be involved in a multi-distributed table join if one of the tables is a round robin distribution, and we discussed data movement in another video later on. So here is the create table command. You've got the database name, the schema name, and the table name. You then define a column name and a data type. You can optionally define a collation, nullability, constraints. There are limitations on the kind of constraints that you can use, but we'll look at that later on. And you can define a default with a constant expression. And then after that, you use the with table options, and the with table options we'll go into in a moment, but I just want to make you aware that you can also create temporary tables as well by prefixing it with a single hash. So fundamentally this syntax is the same. The only difference is that you've got a single hash before the table name. The with options, well, basically we've got three options. We can define indexes, which can either be a custom column stored index, a clustered index. We could use a non-clustered index, but there are reasons to be cautious about that, which we'll discuss later on in this video. You don't need an index at all, in which case it will become a heap. And a heap is essentially a table without a clustered index. The second option is to define a distribution. We've just discussed the difference between hash and round robin. And you can also define a partition. And we're going to cover all of these three areas. Well, we've covered distribution already, but we're going to look at indexes and partitions in more depth later on in this video. So here's an example of a create table, my table. We've got a concord ID, which is an integer if not null. We've got last name with a varchar 20, and we've got zip code of varchar 6. Notice there's no distribution clause defined here. If you were to create a table without the distribution clause, it always defaults to round robin, so please be mindful of that should you be troubleshooting any environments in Azure SQL Data Warehouse. There are limitations to creating a table. There's 2 billion tables per database, up to 1024 columns per table. The number of rows is only limited by the available storage, and the maximum bytes per row is 8060 bytes, which is a typical SQL Server limitation. There are limitations on data types as well, so most scalar data types are supported. You'll find the main exceptions are kind of blob data types like text, XML, SQL variant, timestamp, system and common language runtimes, UDTs. Identity columns and primary keys and foreign key constraints are not supported. And be mindful that this is constantly changing, and they are on the roadmap, so they're going to watch out for changes in this area soon. So although today I'm saying that these features are not available, that doesn't mean to say that they will not be available in the near future. Collations are fully supported, and they are available on the column level as well. There is a default, as you can see on the screen. So as we mentioned with constraints, the only constraint that is supported at the moment is a default constraint, and these can be defined in a create table and an alter table, but it has to be a literal value or a constant. At the moment, primary keys and unique indexes are not supported, and foreign constraints are not supported as well. But as I mentioned before, these are on the roadmap and could change at any time. With the alter table command, we have the ability to modify, add and drop columns. The columns that can't be modified or dropped are columns that partake in as a distribution column, either part of an index, either a partition column. But there are techniques that we can use that we'll look at on another video, where we may have to recreate a table based on an old table because we want to change the distribution column. We want to create a different index or a partition. We've also got the ability to perform partition management, where we can rebuild all the specified partitions, and we also have the capability to support split, merge and switch operations in partitioning functions as well. So that gives us a lot of scope when it comes to loading. So here is the syntax for alter table. Again, very similar to what you get on-prem. You can define the table name, then you can go into alter column with the type, the collation, the nullability. We can add column definitions, column constraints, drop columns and constraints, and then we can rebuild partitions either based on partition number or all of them. We can split and merge partitions based on boundaries and switch partitions as well. Column definitions can change in terms of the type, a constraint or nullability. And there's also support with truncate table, which works with distribution tables, whether they're permanent or temporary tables, but you can't use the truncate table with explained or within a user-defined transaction. So how do we create tables? Well, what we're going to do this time is open up Management Studio. Now, I do most of my work in Visual Studio, and I recommend that you actually use Visual Studio when creating all the objects within Azure SQL Data Warehouse. But a very common question I get asked, and I get asked this from a lot of DBAs, is, hey, can I use Management Studio? So what I'm going to show you here is that I can actually connect up to Management Studio. I'm just typing in the password, and oops, which means I've got the password wrong. So let me put that in. So we're connecting to the instance that we just created in part. And as you can see here is the equity database with no tables at all. Now the thing to bear in mind is, whilst there's things that you can do in SQL Server Management Studio, there's not full compatibility yet with Management Studio, but as I say, watch this space for any updates that are going along. So what I could do is right click the equity database, do a new query, and that will create a new query, a file. And you'll notice that for Azure SQL Data Warehouse, there's certain settings that need to be set in order to be connected, but I'm only going to do it for this session only. So ordinarily, if I basically look at creating tables here, ordinarily I would run this script from within Visual Studio, but because I get a common question about could I do that kind of activity in Management Studio, what I'm going to do is paste that code in Management Studio. Basically I've got three tables. The first table is called Business Hierarchies, and there's Book ID, Division, Cluster, Desk Book, Volcker, Region. Think of that as just a hierarchical structure of information breaking down data into hierarchies. Notice there's a clustered column store index on this, and I'm using the distribution of round robin. So if I highlight that code and execute the code, the command is completed successfully. We have the very familiar dates dimension table, broken, it's variations of a date. And like the business hierarchies table here, we're using round robin with a custom column stored index. If I execute that, this completes successfully. And then finally, we've got what is the equivalent of a fact table. Equity time series data with date, book ID, profit and loss, var, lore, and we've got a custom column stored index with a hash of P&L. So what I'm going to do here is I'm going to execute this query, and that command completes successfully. So if I refresh the tables here, we basically get the 3 tables that we've just created. Notice the tables with round robin have a little yellow diagonal stripe going across those table icons, whereas with hash we kind of have that table split. So that's how you can view it visually. And like SQL Server Management Studio, you can right click and then select top 1000 rows, and this is really just to confirm that there is no data in those tables at the moment. So what about indexes? Well, the indexing options are, you can have no index at all, in which case you've got a heap. But Azure SQL Data Warehouse does take advantage of the column store technology that was born out of on-prem SQL Server. And we can make use of the traditional indexes as well, clustered indexes as an example. So clustered column store indexes is a technology that was introduced in SQL Server 2014, and they're designed for data warehouse type queries. Column store itself came with 2012, but it was a read-only operation, and it's evolved in SQL Server into into what we got custom column store, and this is being used in Azure SQL Data Warehouse, and it is optimized for data warehouse type queries. So what it does, it enables queries to be isolated more efficiently over the column compared to what you would have with the traditional B tree structures that you would have with clustered indexes. We basically get a higher compression ratio due to the structure of the custom column store index. So page compression is typically 2.5 to 3.5 greater. Column store is about 5 to 15 times, depending on the data that you're using. So basically we get higher usage of storage and a greater return on investment. We get new batch mode processing within that, which gives lower CPU utilization with the same number of rows. And it can support existing data warehouse functionality as well, such as partition, switching, splitting and merging. So data manipulation language is supported in custom column store, and it does this because basically we've got what's called a delta store, and what that basically means is that inserts are added to the delta store first, and then when approximately 1 million rows are hitting that background, the contents of the delta store are then placed within the column store itself. Deletes from the column store are logical, so they're not physically removed until a rebuild operation is done. And an update is a combination of an insert and a delete. So fundamentally you'll get an insert occurring in the delta store, a logical delete occurring in the column store, and then with a 1 million change in the delta store, they get placed in the column store, and with a rebuild the logical deletes are physically removed. So converting a delta store to column store can be done with a reorganize, and it's an online operation as well. We've got support for add, drop and alter column as well, and partition switching is done here. So clustered indexes versus custom column store index versus heap. Which one do you go through? Well, heap tables are really good for inserts. So for initial loads with a table that's got round robin as its distribution, heap tables can work really well. So don't rule them out completely. But really, when it comes to the final data warehouse, you're going to angle for clustered column store indexing in the first instance, simply because they offer the highest compression and they are actually optimized for data warehouse workloads. Clustered indexes, they can introduce a sort step in table load. So it's slower than a heap, but it could organize your data. But it does require periodic maintenance as you get fragmentation, but this is done through a create table and selector, a CTAS statement that we talk about in another video. So really, I guess in summary what you're looking at is for an initial load where you're not getting to the final data warehouse, heap tables work well. For the final data warehouse, particularly with fact tables, custom column store indexes work well. But if you've got intermediary steps between that, clustered indexes can support the sort step order there. Non-clustered indexes be wary. They become fragmented with data manipulation language, so you need the alter index to defrag that. It can affect the performance of the ML operations. The reason for that, if you're familiar with B-tree structures, is that not only are you adjusting the heap of the data in the clustered index, you're also having to modify the non-clustered index as well. And because the non-clustered index has a separate B-tree, you're effectively taking up more disk space. So really, you got to use this judiciously, and it's kind of a last resort when concurrency is really important. So we'll talk about statistics now. Every indexing object that you create will create a statistics object. So what are statistics? Well, they are database objects, and fundamentally they contain statistical information about the distribution of values within a column. So there's a histogram of information that tells it about the distribution of data, which can then lead to the selectivity of data and the density of data. Now, be aware that multi-column statistics can also be generated. And this is where the density information becomes really, really important, because it provides the correlation of values between those columns itself. So statistics are really important because it provides the map of where the data is, essentially, that Azure SQL Data Warehouse can use to aid it retrieve data in a performant manner. Now, there's something to be mindful with statistics on the compute node and the control node. The statistics on the compute node, well, basically there's an automatic statistics setting on the compute node, and it's done through standard SQL Server sampling. But the statistics on the control node, whilst there are statistics there, they're not updated manually. And that's really important because the control node is what takes the initial hit of the application making a query request. So when a query request is made from a client application, it goes to the control node first. Now, there is a request made by many of our customers to change this, and I know that it's on the roadmap. So even though I'm saying today that statistics are not updated automatically, watch out for any changes in the future. Multi-column statistics. If your joins are on multiple columns, multi-column statistics helps avoid what we call nested loop operations in your execution plans. So, for example, if you've got a long-running query step that has a multi-column join key, and you've got lots of reads, or you've got an estimation plan that's showing a nested loop for a very small number of rows, or you had an actual query that had millions of rows running through a nested loop operation, well, you might want to consider using multi-column statistics that will provide that further information, such as the density information that enables the Azure SQL Data Warehouse to come up with a more optimized plan. The statistics syntax, should you need to create any, is create statistics, define a statistic name. You've got the on clause where you define the table on which it's on, and then you define the column. Now, one of the things that we can take advantage of are filtered statistics, and this is where we can use a where clause within the create statistics statement to restrict or the range of data over which the statistics being created. We can do this in indexes as well. So with a create index statement, we can use the where clause, and this can be rather beneficial. If you've got a situation where you've got, years worth of data, let's say 10 years worth of data, then you may come to the conclusion where, well, you know what, 80% of our queries are going towards 20% of the data, which is the last 2 years worth of data, as a crude example. So what we might do is create statistics and create indexes with a where clause that restricts it over the last 2 years, and that can basically reduce the surface area over which the index and the statistics are based, which means you get more accurate information about the distribution and density and selectivity of data in there, which can inform the query optimizer more fully of what data is where, which means you get better plans, so to speak. So don't rule out filtered statistics and filtered indexes to help improve performance as well. The best practices for statistics is, we now know that there's 2 levels of statistics. There's statistics on the compute nodes and the statistics on the control node, and at the control node level the statistics are not maintained or created automatically. So the goal is to update statistics for best cost-based optimization. Now if you drop and rebuild an index, that's going to refresh the statistics for you, but in an initial load you're going to have to create statistics straight after that load because it's not done automatically for you. This could change in the future, but at the moment that's not the case. So what's the solution? Well, you could create statistics for all columns used in joins, group by and where. That's smart, it's targeted. If you want to be lazy, you could just do statistics for all columns in all tables. So that's the kind of taking a hammer to crack a nut approach. But of course, the more statistics you create, the more database objects you have, the more it's got to search. That can actually have implied overhead. So for me, always go for option 1 first, unless you've got scenarios where it's not feasible to do that. And then we move on to partitioning. And with partitioning, we've got to talk about how that is different from distribution. Now we know that the data within an Azure SQL Data Warehouse is already spread. You've created your SQL Data Warehouse, you've created a database, and within that database you've defined a service objective, otherwise known as data warehouse units, either from 100 to 6,000, and that determines the number of nodes that you will have in your Azure SQL Data Warehouse. We know we're always going to get 60 distributions, and we know with DW100 we get 1 node, so there'd be 60 distributions on a node, but if we went up to DW300 we would have 60 distributions spread across 3 nodes, so that's 20 distributions per node. And then through the create table statement using round robin, we will get an even distribution across all the distributions across the available nodes. So we're already segmenting data by distributions already. So what does partitioning add? Well, partitioning adds, if you will, a horizontal separation of the data based on what's known as a partition function. So this enables operational efficiency when we're adding, loading, dropping or switching data between partitions. In short, partitions are really good for fast loading of unused partition and then switching it after an initial load. And the reason we do that is because partition switching doesn't physically move the data, it's a metadata switch. So whilst it gives the appearance that data's actually being moved, it's not. Metadata in that partition is being switched to give the appearance that data's been moved. So partitioning is really good for maintaining data or indeed switching data very, very quickly. So the partition table usage, it's the same rules and guidelines as a standard on-prem SQL server. So you use partition switching for large inserts, updates and deletes, and you can use metadata queries to explore the partitions, such as the number of partitions you have, the boundary values you have, and what the partitioning column names are. So partition table management provides the ability to create, merge, split and switch partitions, and DBAs will be very familiar with this for large tables, because what it does, it enables you to take large table, horizontally partition it into smaller chunks, and then from that you can choose to load data, archive data and take a sliding window approach. So partition table management works really well for optimizing the loading of large tables, and when you combine that with the fact that we've got filtered indexes and filtered statistics, you can then target and align your indexing strategy with your partition management to enable piecemeal data reorganization itself. So to create a distributed table with partitions, you've got the standard create table statement with my table. You define your columns, your data types and any nullability, and in the with clause you'll define your distribution, whether it's hash or round robin. You'll define the index that you're using. In this instance we're putting a clustered index on ship date, and then we are using a partition on the ship date column, and range right for values. So we've got it for the 1st of January 1992, the 1st of February 1992, the 1st of March 1992, the 1st of April 1992, and so forth. That's all you need to do in Azure SQL Data Warehouse. In on-prem, you'd have to create a partition scheme and a partition function first before you can make use of the partition within the create table statement. Not the case in Azure SQL Data Warehouse. So that is something that you may come into conversations with customers where they'll be very used to taking that approach with on-prem. No need to do that on the Azure SQL Data Warehouse. So partition tables with clustered indexes could improve range queries if you do it correctly. But bear in mind, you may want to consider dropping a clustered index while doing an initial load, because if you have the index on while you're doing initial load, not only does it have to load the data into it, it also has to reorganize the clustered index. In fact, a clustered index, the leaf level of that is actually the data itself. So in the takeaway from this is, clustered indexes are brilliant for helping reading range queries, but if you're going to load data in, it will hinder data load time. So it's usually typical to drop the clustered index, do the load, then apply the clustered index after. It can also lead to page fragmentation as well, which can hinder performance. Partitioned table with a custom column store index will improve range queries, but compared to a cluster index, a custom column store index does have the lowest memory footprint because of that compression ratio that was talking about as well. Partition tabled with non-cluster indexes, avoid. If you have to, do it with a lot of testing. It could be used to potentially aid better concurrency because you'll create non-clustered indexes that are targeted to specific queries, but it's not guaranteed, which is why we're saying you should do a lot of testing. So it can cause a lot of random IOs. So last resort, only if you're doing it for better concurrency. Use partitioning for manageability. That's the whole point, maintaining data. So typically you'll specify partitioning on a date key or an integer surrogate equivalent. Typically it's the same as a clustered index key, so you can get that alignment, and then you use this ultimately to switch partitions out for fast deletes, in to modify or have a historical slice, or in if the data being used is you want a separate copy of that for a separate environment such as dev or test. So if you're on the in-person event, you'd be doing a lab on this right now. Essentially, there are questions that I would ask attendees on my course to consider, and I would ask you to pause this now if you want to review it as a review of this video. A summary, what have we gone through? Well, we've gone through Azure SQL Data Warehouse databases, where we've talked about the addition being important, the max size being important, and the data warehouse units being important. We talked about distributed tables, the difference between hash and round robin, and when you would use one over the other. We talked about indexes and how you manage those indexes, the fact that we can use clustered column store indexes, clustered indexes. We could also use a heap, so we don't need indexes at all, and how that's useful for initial loads, and the fact that really you should be avoiding non-clustered indexes. We looked at statistics and how these are objects that sit on top of the indexes and provide information to the query optimization process about plans that can be used to get the data, and we finished off with working with partitions. More information can be found at learnanalytics.microsoft.com. If you go to the training tab in there, or the analytics training tab, you will be able to see a list of in-person training events provided by people from Microsoft or from our partners, and there is self-learning there. We've also got the Cortana Intelligence Gallery as well, so we've got a number of examples in manufacturing, banking, retail and healthcare, so I do recommend that you look at some of them. Some of those solutions do contain Azure SQL Data Warehouse as well. Thank you for your time today, and hopefully I will see you on the next video. Data loads. We'll look at monitoring data loads and provide you with some code that you can use to do that. And then we'll look at how Azure SQL Data Warehouse can interact and integrate with Azure Data Factory. And then we'll wrap up with some recommendations. So, the load user is probably one of the first objects that you'll create once you've provisioned an Azure SQL Data Warehouse and created a database. And with the load user created, you would then use that user account to perform the loads. Now, it's one login that you create, and you map that login to a database user, and you effectively give that user service admin permissions, so it's kind of full SA permissions. And one of the things that this does is it provides fixed memory assignments dependent on the data warehouse units that you choose, but it's a very, very important point. There are additional benefits. So the fact that you've got a dedicated load user means that you can monitor the load requests a lot easier when looking at monitoring queries. It gives you a more granular permissions model. So basically you're mindful of only giving the permissions that the account needs rather than everything. And as I mentioned before, it provides flexible memory management by determining the amount of memory per distribution that the load user will get, and this is impacted by other things that we'll look at in a moment. So the first thing you're going to do is create a login, and that's done at the instance level. And in this case, we're calling the login name, and we're using the password of SQLB1TS exclamation mark. Now, with that login created, you'll then map a database user to that login. So in this case, we've got a user called create user called username for the login called login name. And one of the first two things that you'll do is you will add that username into database roles called login manager and DB manager. And this is done by using the system stored procedure SP add role member. Now, once you've got the login created and the username created and they're added to the roles, there is one more thing to do against the database, and I'll cover that in the next set of code. But I do want to talk about what is called resource classes, because this is really important to the memory assignments that you will give essentially to the dedicated load user. Now, on the left hand side, you've got 4 resource classes available. It's called small RC, and RC stands for resource class, medium RC, large RC, and X large RC. And you can list all these resource class roles by running the following query against the object sysdatabase principles and filtering where type desk is database role and is fixed role equals 0, and they will list the roles for you. Now, essentially, with that in mind, there's then a little bit more work to do with that user. So the first line is mapping the database user to login name that we saw in the previous code. You've already added them to the login manager and the DB manager, but what you're also going to do is you're going to grant control on your database. So in this instance, we're granting control on database called MySQLDW to username, and that's the name of the database stored in Azure SQL Data Warehouse. Now, the select statement in the middle really is listing the role principal names and the member principal names for each of the roles for medium RC, large RC, and X large RC. But once you've granted control to the database, what you can then do, or what the final step is you're going to add that load user into one of those resource class roles. And in this example at the bottom, we're using the system stored procedure exec SP add role member, and we're adding the username to the role of medium RC. So they're the steps that you need to do post provisioning of your SQL Data Warehouse and database to create your dedicated user. You can identify any users with elevated requests. So this query is really useful when an Azure SQL Data Warehouse is up and running, and maybe you're coming in to troubleshoot some problems with it. And here you can get the breakdown of the request ID, the command, the status, when it was submitted, when it was started, what wait duration is, and what resource class is being used. Sometimes on customer engagements, we find that customers may not be using the appropriate resource class for loading data in, and this is a useful query to run just to establish what resource class is being used, and then to make a decision on whether or not you should change that. Now, as I mentioned, resource class has an impact on the amount of memory that is used. And on the left-hand side, on the axis, you can see the 4 resource classes, which is small RC, medium RC, large RC, and X large RC. On the bottom axis, we've got the megabytes per distribution. And on the right-hand side, we've got a legend for the different data warehouse units that are available. Now, in short, if you map a load user to small RC, then regardless of the data warehouse units that you choose up to 2000, you are basically going to get 100 megabytes per distribution. And as we discussed in a previous video, you'll always get 60 distributions. So 60 times 100 is 6,000 megabytes. So basically, with small RC, regardless of the data warehouse unit you use up to 2000, you're going to be fixed at that 6,000 megabyte limit from a memory point of view. So bear in mind that really at a small RC level, your impact is you'll get more nodes the more data warehouse units you choose at a small RC level, and we discussed nodes in the first video of this series. So if I give you one example, if you were to add your load user into the role large RC, and then you were to set your data warehouse to DW2000, what that then will give you is 3,200 megabytes per distribution. So fundamentally, the resource class is as important as the data warehouse units, because the combination of the data warehouse units and the resource class is to impact the amount of megabytes per distribution, plus just switching the data warehouse units will increase the number of nodes that you will get within your data warehouse. Now, for most organizations, we find that medium resource class is ample enough for loading data. We do have occasions where it's constrained, we may go up to large resource class. So let's have a look at the loading options that are available. Now, effectively, we break the loading options down into 2 areas. We've got parallel loads and we've got single gated clients. Now, parallel loads uses technologies such as Polybase, and you can use components of Azure Data Factory that runs Polybase under the hood. Single gated clients include bulk copy program or insert bulk, SQL bulk copy, SQL Server integration services, data flows, and there's some components of Azure Data Factory that are single gated in nature. What does single gated mean? Well, imagine that the client on the left is a SQL Server integration services package. When it loads data into the Azure SQL Data Warehouse, it does this through talking to the control node. Now, we can slightly improve performance by adding multiple sys packages that are executing at the same time. But because they're all communicating with the control node, we're essentially getting a bottleneck at that level. So this can hinder your loads. So fundamentally, what we use is parallel loading with Polybase, and effectively what Polybase does, it addresses more than just the control node. It actually works with the compute nodes and the storage nodes to such an extent that each compute node will talk to every Azure storage blob within the storage node, so that you can get full parallelism of loading the data. So if performance is your key metric for success of loading data within Azure SQL Data Warehouse, then you should use Polybase. So what I'm going to do is, in this example, show you an example of a single gated client to load data. From here, I will log into the Azure portal. So within the Azure portal, we created a SQL Data Warehouse instance called CTO MSFT ADS SQL SRV. If I click on that, that's going to take me to the blade for that particular SQL server. And the first thing I'm going to check is just make sure that my firewall is enabled for this client, because it's been a while since I ran the last video. So in this instance, if I go to firewall, all I'm going to check in the firewall blade is that the IP address that I have here matches the IP address here. And in this instance, what I will do is confirm that that is fine. That's great. And also what I'm going to do is just click on the properties here. And within the properties, I'm going to pull the fully qualified domain name of the server and just copy that. So we'll go into Management Studio, and what I'm going to do is connect to the database engine of the local SQL Server instance. And within this instance, we've got a database called EquityDB that's got 3 tables that are populated with data. So for example, if I select the top 1000 records for dates, this will return back a query that will show me the dates in there. And dates is effectively a dimension table within this very simple data warehouse. My intention is not to blind you with science with a complex data warehouse. There you go. So what we're going to do is connect up to the database engine for the Azure SQL Data Warehouse. We'll just put in the password there, click on connect, and then from this we will expand the databases. And from previous video we did create a database called EquityDB. This has 3 tables, and as you can see we've got business hierarchies dates and equity time series data, and within here we have no records in it. So this is an example of us moving data from an on-prem server to an Azure SQL Data Warehouse server by using a single data client. Now to show you that, we're going to drop into Visual Studio, and within Visual Studio I have a sys project here with a package called package. Let's double click that. Now this package has simply got one data flow, and there's 2 connection managers. One is to the on-prem SQL Server instance, SIR3CTO Redmond. We'll just test the connection there. And the second is called Reading, but it's to the instance of Azure SQL Data Warehouse that we've created. What I'm going to do here is just put in the password, test the connection, and then confirm that that's all fine. Now, as I say, I'm not here to blind you with science. If I go into the data flow, we literally have source connections using the SIR3CTO connection manager. So for business hierarchies here, there's a connection manager, and then we're using the Reading connection manager here for the connection to Azure. And what we can do is execute this task. And you can have any number of transforms in between here before loading it in. And this is really just showing you that you can use sysload data into SQL Data Warehouse, but because it's a single data client, it's not the most performant. One consideration that you might have, if you've already got a lot of sys packages that are loading into an existing data warehouse, my recommendation would be that you change your destination data warehouse to files, and have the destination of those sys packages to files itself, because using Polybase we can pick up those files and efficiently load data, and this is particularly important for huge volumes of data. As you can see, we've loaded the data into the data warehouse relatively quickly in this simple demonstration, but we're only dealing with 27 rows, just over 2,000 rows, and nearly 50,000 rows. So sys is going to work with those volumes really well, but once you start getting into big volumes of data, that's when you start to see the performance of sys really suffer. So in summary, if you've got massive volumes of data, or big volumes of data even that's going into the gigabytes, you might want to use your sys packages, refactor them to output to text files, and then use Polybase to load those text files into your data warehouse, because it will do it in minutes. So we'll stop that package, and that package executed successfully. We'll go back into Management Studio and run this query against the data warehouse, where we get confirmation of the records being created. Now we're going to go back to the deck. So what is Polybase? Well, essentially, Polybase contains 3 core objects that you need to create. Now, ultimately, what you're doing is you're effectively creating what's called an external table. Now, the external table, you can load data into it by importing data into it through what's called a CTAS statement or a create table as select. We'll cover that later on, but essentially external tables are objects that provide structure over unstructured source data. So in order to link to that unstructured source data, external tables need 2 supporting objects. Firstly, you've got the external data source, and the external data source provides the connection information, if you will, to the underlying source data, and this is typically files that are stored in Azure Blob Store. And the second supporting object that you'll create is what's called an external file format, and the external file format is there simply to provide structure to an unstructured or semi-structured file. These 3 together basically provide the object required to take advantage of Polybase. So an external table is simply a metadata table to describe external data. It doesn't hold data at all. It simply provides the metadata over the top of the source data. So if you delete an external table, you don't drop the data in the underlying source, you just drop in the metadata driven table itself. And the reason we have external tables is it gives us Azure SQL Data Warehouse this ability to access data beyond the internal database itself, and perhaps and get data from Azure Blob Store. So this is what's giving Azure SQL Data Warehouse the ability to work with unstructured and semi-structured data. For those of you that are familiar with Hadoop, you could say that external tables has a very similar behavior to Hive external tables in that they're metadata driven tables as well. Now you can query information about external table metadata. There is a specific system object called sys.external_tables, and you can actually query sys.tables as well to view those external tables to give you information about them. So how do we create an external table? Well, here is code that's remarkably, well, it is T-SQL. The only difference here from a create table statement is we've got the word external in there. So we've got create external table, we define a schema name, we define the name of the table itself, we've got the column names, the data types, and the nullability. Now where Polybase gets involved is in the code below the create external table definition, because what we do is we start off with a with clause, and then the first thing we'll define is the location of the where the file is located itself. And what we then do is refer to the data source object and the file format object as we've created them by their names. So just like an external table has a name, the data source object will have a name and the file format has a name. And we just point to those object names, and this will provide the data source connection information and the file format and the structure in which it should be. We can also define reject types and values for any information that we want to reject as well. So an external data source begins with create external data source, and you give it a name. Now in this instance, this is called my Azure data source. So that object name essentially will be placed in this part here. So my Azure storage name, we're going to refer to it in here. So in this instance, what we're doing is we are using the type of Hadoop. Now, that doesn't connect to a Hadoop cluster directly. What it does is Hadoop uses Azure Blob as well. So you may use Hadoop to store unstructured files in Hadoop but that is stored essentially in Azure Blob Store within the Hadoop cluster. So even though the type is Hadoop here, you're actually specifically referring to the underlying Windows Azure storage blob. So fundamentally, if you've got a Hadoop cluster with unstructured files, look at the Hadoop cluster configuration, look at the Azure Blob Storage account names that are there, and you can refer to them in here. So effectively, with the location, we're pointing to Windows Azure Storage Blob. And if you've got a container, put the container name here, and then define the storage account name .blob.core.windows.net, and then any path that you've got. That will all be encapsulated within the My Azure Data Source object. Now, when it comes to the file format, we use create external file format. In this case, it's called ORC file format. And here we've got format type of ORC, which is optimized record column. And then we're pointing to the data compression codec, which in this case is default codec and snappy codec. And this is an example of a file format defined for optimized record column. Now, there are other formats. So we've got Parquet for file formats, and this is an example of creating an external file format called Parquet file format. And again, we put the format type as Parquet and the data compression pointing to the relevant codecs. Be mindful that there can be data type mismatches. So, for example, when it comes to RC or Parquet, if you've got a SQL type of date, the recommendation is to use timestamp. You could also get different ranges as well. So in Hive, a timing goes from -128 to +127, whereas in SQL it's 0 to 255. So these are things that you're going to have to be mindful of there. We've got an example here of a delimited text, which is what a lot of people will use. So we're creating an external file format called my text file format with format type equals delimited text. And with delimited text, we've got format options such as the field terminator, the string delimiter, the date format, and whether you use the type default, and then the data compression with the relevant codecs in there. Be mindful that with delimited text guidance, use UTF-8 to encode your files. We are being asked by customers to use UTF-16. That is on our roadmap, so watch this space. Things can change. I've said that on a number of videos, so make sure you keep up to date with the updates that we have, and you can do this through the product group's webpage. Row delimiter is not configurable. No row delimiters in strings, and use gzip, not winzip for compression. Date formats, be mindful that there are implications of date formats here, and basically if you want to use date time, you express it within the delimiter code as YYYY-MM-DD, and then you specify your hours as HH:MM:SS. There are other examples of the different date times that are there that you can use. Be mindful that you can only have one data type, one date format per external format file. Okay, you can't have mixtures. So let's have a look at an example of loading data with Polybase. So we'll choose one example here, and we'll go back to Management Studio. And within Management Studio, we are going to delete the dates table. So that dates table is now dropped. And to use Polybase, the end game is we're going to take the data that basically mimics what's in the on-prem here, but effectively what we've got is, instead of addressing a table of that data, imagine we've had a sys process that has created a file of those dates. And that goes back to my recommendation of refactoring your sys packages to take advantage of Polybase. So rather than, I'm going to show you how I've done that. So you should know how to export data out of sys into a text file. And basically within that, what we've got is in here, we've ended up with dimdates2.txt, and this is the data. So imagine that a sys package has taken that from your on-prem SQL server and just dumped it out. Now, within the portal, what we're going to do is, rather than create a full Hadoop cluster, we're going to check what storage accounts we've got. Okay, so we've got no storage accounts at all. So I'm going to create a storage account. So I'll click on plus to add new. This will bring up the services category blade. And what I'm going to do is just type out storage account. Click on storage account here. And then from within here, I'm going to create an Azure blob storage account. And think about this. It's, imagine you've got a Hadoop cluster. Your Hadoop cluster will automatically provision these storage accounts underneath the hood. So from this case, what we're doing is we're bypassing the full Hadoop cluster because it'll take too long to create, and we're just going to create a storage account, and it's designed to mimic data that you've got in a Hadoop cluster. So what we're going to do is we're going to define the name of the storage account first, CT or storage account. We've got the deployment model that we'll use as resource manager, and we're going to set it as blob storage. We'll leave the performance the same. We'll set the redundancy to local redundant storage. We'll leave the access tier the same, the storage service encryption the same. And what we'll do is we'll assign it to a resource group that I created for the purpose of these videos. And we are going to choose CTO ADS Prep RG stored in North Europe. There are other videos out there for storage account management, so I'll leave it at this point. What we'll do is click on create. This is going to validate the configuration that I've set, and it's going to create the storage account for me. The deployment has started. We'll just wait for that to complete. So the deployment has been completed. So what we're going to do now is go to all resources and do a search for the storage account that I've literally just created. And there is the storage account. So we'll click on the storage account. Now what I could do is I'm going to transfer the text file into the Azure Blob Store. Before I do that though, is one of the things you can do is organize your storage accounts into containers. So I'm going to create a container within this storage account, and I'm not being I'll call it data container, and I'm going to leave the access type as private, which means I need a key to access that. So there's the data container. Choose OK, click on create. And here is the access key that I was talking about. If we click on the access key, what I'm going to do is copy the first key and then just open Notepad up and just basically keep that key in there for use later on. So now I've got the data container within the CTO blob store. What I can then do is click on that container, and I could use AZ copy to do this if I wanted to, but I'm going to upload that dimdate2 file. So let's go into here and then browse to the file that we've created. And there's dimdate2.txt, and we'll upload that. The upload is completed, and as you can see here, dimdate2 is in the data container location within the CTO storage account.blob.windows.net, and I'm going to copy that as well. And I'm going to put this in my Notepad document as well. So that's the prep work done. We've effectively taken a sys package and outputted the data as a text file in Azure Blob Store. Now we can use Polybase. How do we do that? Well, what we're going to do is we are going to do this in Visual Studio. And in Visual Studio, I'm going to open up a file. So I'm going to connect up into Visual Studio and then log in as the Lord user. Okay, so we've got confirmation there that we're actually in the right database. And what we're going to do now is change the database to the Equity DB, because this is where we're doing the loading. So we've now changed the context of that. Now, the first two steps we're going to do is a one-off operation the first time you're going to be loading data. And what you've got to do is you've got to create a master key that will encrypt credentials that you'll be sending to connect to the Azure Blob Store. So the first thing we'll do is we'll create a master key and we'll execute that. So that's completed successfully. So once we've created the master key, we're then going to create a database scope credential, and this is really important. The database scope credential can have any name that you want. And there's two settings to put. The identity, which I'm really not bothered about. Really not bothered about the identity at all. You can call it whatever you want. What I am bothered about is the secret. And the secret is essentially the access key for the Azure Blob Store. So if I go back to my Notepad document, and within the Notepad document, we grab and copy that key, we can paste it in here, and this is how it's going to use the database scope credential called Azure Storage Credential, and it will take that key and present that key to the Azure Blob Store. So let's execute that. That's completed successfully. So those first two steps have got nothing to do with Polybase. It's setting up the security for providing access, and they're one-off operations essentially. So now we create the supporting objects for Polybase. We've got an external data source called Azure Storage with the type Hadoop, but as you've seen, I've not created a Hadoop cluster. We very specifically put the location as Windows Azure Blob Storage, data container at ctostorageaccount.blob.co.windows.net, and that is what I've literally just created in front of you. Notice the credential is the Azure Storage credential that we have quite literally just created right here. Let's highlight that code and execute it. The command completes successfully. Now we've got the data source, we're now going to create the file format. And I opened up the file and it was the date information. So we're creating the external file format, text file, with the format type of delimited text and the format option, and we're just specifying a field terminator here. Let's execute that. So now we've got the supporting objects for the data source, and that data source is pointing to a credential, and we've got the external file format. Now we can actually import the data using Polybase, and we do this by using a CTAS statement or a CETAS statement. A CTAS statement is create table as select. A CTAS statement is create external table as select. And what you'll notice here is that we've got a standard create table statement, but it's got external in it with the columns, the data types, and the nullability. But within the with clause, we start making reference to the polybase objects. So location is the root of the path that we've defined. The data source is Azure Storage, and the file format is text. So these refer to text file, and it refers to Azure Storage, and Azure Storage, as we know, refers to Azure Storage credential, which is up here. So there's dependencies on a number of items here. Now what this will do is, if we run all that code, it will create the external table, which is a metadata table. So let's execute that. That's completed successfully. So what we can do now is we could run a query against that. But bear in mind that the external metadata table is a metadata table. The actual data that it's querying is in the underlying text file. So 2192. We can then select all the columns if we wanted to. So we've got the full raft of T-SQL at our disposal here. But the important thing that we're trying to do is we're going to create a table. And we're doing this with a CTAS statement. Okay? So basically we're creating a table here. Whoops. As select. And that table will be called DBO dates. And if you saw the second video in this presentation, we talked about indexing and distribution. So we'll do that. Execute that. That command has completed successfully. What that means is we've done a select of that external table that we created earlier called dimdate2external, and dimdate2external we've literally just created here, but it's going ahead and creating a table called dimdate and using the table definition of dimdate2external to do it. So if you saw video 2, you know the very first thing you should do once you load is create statistics on the data where you feel is appropriate. So we'll just do that, create those statistic objects. Those have been created, and we'll go back into Management Studio where we will go to the data warehouse. We will refresh the tables and query the dates table, and we have successfully used Polybase to load data in this table. So this is something that you might do for initial loads as an example. So let's go back to the slide deck. Now orally, if you're in my in-person training event, you'll be doing this yourself. But we're going to move on to importing and exporting data, and you've seen this already in the previous demonstration. In the previous demonstration, we looked at a CTAS statement, and this is what we did to create the final dimdate table. Create table temp fact online sales with distribution and custom column stored index as select start from your ASB fact online sales. And you've got an option there to put labels in as well, and we'll talk about that in a moment. So we've got a label here called CTAS import. But you've seen that for yourself with the demo that I've just done by importing data into the data warehouse for the date dimension. We can also define partitioning during that CTAS. So as you saw in the previous statement, we've now increased this with a partition clause, where we define the column on which the partition will be based. In this case, it's date key here. So in this case, it's date key, range right of values, and then we're defining the ranges in there. We've also got the ability to export data with CTAS. You saw the CTAS statement in the demo that we've just done, and that was done to create the external table. So here is an example of that from a code perspective. Again, we're using labels. And labels are useful because you can add labels to any code that you do, whether it's a select, insert, update, delete, ctas or ctas statement. And we can query sys.dmpdwexec requests where label equals and put a clause in there, and from that you can pick up a list of operations. So labeling is quite a useful technique to use. So what about monitoring data loads? Well, effectively there are occasions when data loads go wrong. So here are a few statements that you can run to give you information. So firstly, how can we monitor execution requests? Well, there is a dynamic management view that you can use called sysdmpdwexec requests. Here you can get information pertaining to the operation, what steps have been done. Well, you'll notice there the location, the step is actually null at this point. What we're interested in here is the duration, the start and the end time, and how long it took, and what resource class is being used, and capturing the command that's been executed. Now, if you want that step information, you can add the step index and the location type columns from the a different dynamic management view, which is dmpdw requests steps, to add that additional information there as well. And then you can bring all this together through a join. So you can join essentially the PDW SQL request with the PDW SQL request steps together to bring all that into one query. And this will give you a breakdown of the various steps and requests that have been done during your loads. Monitoring worker activities. So workers are basically components within Azure SQL Data Warehouse that will perform the work. So this query is done by using the dynamic management view called sysdmpdw DMS external work. And here again you want to get things like the start and the end time, the throughput, the duration, and what worker is being used itself. There's a whole raft of monitoring tools that you can use and code that you can use to do this. Please do investigate this, but be mindful that here are some that can help you look at the activity that's going on. So moving on, we're going to look at Azure Data Factory integration. So Azure Data Factory is a technology that's part of the information management category of technologies, and it's responsible for orchestrating the movement of data between various data sources and data destinations. You can also use intermediate data sinks, as they're called, such as maybe using an Azure Blob Store as a transient storage area for data. An example of that will be you refactor your sys packages to output text files. Those text files are in Azure Blob storage, and then you're calling data from the Azure Blob store to load into Data Warehouse itself. So from an Azure Data Factory perspective, there's 4 components that you need to be aware of. Link services. Link services can provide connection information to data, or it could call compute technologies such as a Hadoop cluster or a machine learning model, and so forth. Then you'll create data sets, and data sets is the structure of the data itself. And on those data sets, you'll perform activities, and activities can be cleansing or transform operations. So, for example, you may have an activity that does a Hive query, and that activity of the Hive query calls the link service that's called a on-demand Hadoop cluster to execute that Hive query to do some cleansing. You may then have a second activity, and that second activity is essentially taking the cleansed data from the Hadoop cluster and then loading it into a machine learning model. So really, that slide's wrong actually. I'm going to change that slide and just move that out a bit so I can do that, because pipelines are really a combination of multiple activities, and I don't mind making changes during a presentation like this, You got to see a pipeline is a collection of activities, and the thing about pipelines is that you can schedule a pipeline. So fundamentally, that will schedule the activities underneath it, and more importantly, you can monitor pipelines as well. So yeah, just a correction there. I would say that pipelines is a collection of activities that do given tasks, and activities relate to data sets that it's going to manipulate and to link services that calls the source of that data set, or indeed compute resources that will perform some work, such as a Hadoop cluster performing a Hive query, or indeed you may call data lake to perform a new SQL command. Now, from a Polybase perspective, when you're creating a linked service, it can only go to Azure storage at this point in time. So this goes back to the point we were making with regards to creating an external data source of Hadoop. Well, it's not really calling Hadoop, it's making a call to the underlying Azure blob storage itself. And there's no shared access signature authentication as well. Let me explain what shared access signature authentication is. This is to do with Azure Blob Store. So if I go back into the portal and then go back to our storage accounts, one of the things that you would have seen me do with the storage account is I would have taken a copy of the access key. Now, for the purpose of Azure Blob Storage, you can only make use of that access key to allow a link service in Azure Data Factory to connect. So here's the access key here. And this is what you'll have seen in a previous demonstration where I went over here and actually copied it. Well, sometimes people are really nervous to actually use the access key, and what they'll do is they can make use of shared access signatures to basically have a hash of the access key. So let's say we're going to allow access to a blob, we're only going to allow access to a container, and within that container we're only going to give read permission, and then we can at the bottom here generate a shared access signature key, which will provide a key that gives access to a blob of a container with read permission in this time range for allowed IP addresses with these protocols. Now, unfortunately, what that will do is if you generate that SAS, you'll get this token that you can copy, but unfortunately, Azure Data Factory at the moment in time can't make use of that. It can only make use of the access key. So I think it was better there just to show you the difference of what that means there. So going back to the presentation, what you will get, and with that in mind, you'll get a link service that effectively defines the name for the link service object itself here. Oops. And this is for Azure Blob Store. And within the properties, you'll define a hub name that is a name that's the same throughout all the objects that are part of it. We'll define type of Azure storage, and then the type properties is the connection string, which is the endpoint is HTTPS. The storage account itself, in this case for me, will be CTO storage account, and then you put in that account key here. So firstly, you'll create the link service object to Azure Blob Store. Then you'll create the link service object to SQL DW. Again, you'll give the name to that link service. You'll have a hub name that's the same, but this time the type is Azure SQL DW, and with the type properties, you'll put the connection string. The connection string is a data source as CTO, SQL server, whatever I called it, .database.windows.net. The initial catalog in my case here will be EquityDB. You choose whether you use integrated security, or in our case it's false, so therefore the user ID will be C-tester-O'Neill, and the password will be the password that I have, and then we can define a connect time up and whether encryption is there as well. So you kind of seen me do that in a different way in a previous one. For Polybase, for the input data set, the input data set can only be Azure Blob. The type can only be text format. The row delimiter is new line. The null values is 2 quotes. And the encoding is UTF-8, and there's no escape character or quote character for that activity at all. So this is an example of what an input data set would look like, where you'd effectively point to the blob path, which is data container at CTO storage account .blob.windows.net. The format you'll define as the text format, what your delimit is, what your row delimit is, there's your null, there's your encoding, and then don't forget the compression, which is gzip as optimal. Okay. Alternatively, you could use what's called the copy activity that is new. It's in preview at the moment in Azure Data Factory. Your blob source properties, you need skip header line count is not specified. The SQL DW sync for the slice identifier is not specified, and the column mapping is not specified itself. So you could do the copy activity using a JSON file, and the key point in this JSON file is that you would set allow polybase equal to true here, or alternatively you could use the copy activity wizard, and that's what I'm going to show you. Be mindful there are limitations. So the primary limitation is one-time syncs can't be edited. Right, so I'm going to give you a demo of a one-time sync. Once it's done, I can't edit it. And polybase can't be configured in the copy wizard at this point in time today, but it could change soon because it's a roadmap item. File headers have to be addressed, so ADF validates the data types of data in the source based on that first row. So you might want to remove that, which is what I did in bin date2 text file. Fields must all map to strings if headers are present. So there you go. Headers become strings. And use another copy activity blob to blob to remove headers from the source if you need that step. Avoid column mappings. Input names must equal output names, and data types must match as well. So it's quite strict in its limitations, but you'll see from this demo that it is relatively straightforward to do. So in this instance, what we're going to do is drop out of this and go back to the portal, and in the all resources that you can see here, just filter the resources that we've got. Okay, so the first thing I'm going to do is I'm going to create a new Data Factory instance. So we'll go to databases, and in the featured apps, Data Factory appears at the bottom, and it's very simple to configure a Data Factory. We're going to specify the name of the Data Factory instance, so I'm going to call it CTO-ADF. I'll assign it to the subscription here, and I'll use the resource group that I've been using for all my presentations, which is CTO. And in here it should filter it to adsprep.rg, and I'm going to store it in North Europe. Now it looks as if the Azure Data Factory is only available in 3 regions. What I need to make you aware of is that's fine, because a Data Factory activity can call resources in other regions. Remember that Data Factory orchestrates data movement and relies on other services to perform that movement for it. Essentially, Data Factory just provides the pipelines of movement. So we'll choose North Europe, click on Create. This will create the Data Factory instance. So the deployment is now successful. So what I'm going to do is go to All Resources, filter by my first 3 characters as I usually do. And there is my Data Factory. So we'll click on the Data Factory, and this brings up the Data Factory canvas. Now, this is not a Data Factory video, so I'm just going to go straight to what we're working with. And as you can see here, we have a copy data action that we can perform. In this instance, if we click on this, what it will do is it will bring up a wizard where we can essentially use the wizard to move data in or out of Azure Data Warehouse. So what I'm going to do is, in this example, we're going to take the business hierarchies data and output that out to our blob store. So let's call this business hierarchy BW to Azure blob. We can put a description here. We're only going to run it once, but we could do a schedule of monthly, weekly, daily, hour, and a minute, and we can choose a start time. We're just going to run once now, and we've got an expiry time here. This is 3 hours. I'm just going to leave it as the default. So what is our source? Well, our source in this case is going to be Azure SQL Data Warehouse. We'll click on next. What we need is the connection name. So the connection name, we'll call it CTO SQL DW. And then this is going to be from an Azure subscription. And that Azure subscription is my subscription. And within it, we are going to do CTO MSFT ADS SQL SRV. Okay. Now, the database is EquityDB, and the username is, and we'll put this password. So, fortunately, from within the wizard, we can get all the information that we need. We click on next, and then we're asked for the data set that we want to do. Now, we can use a query to pull that information back, but what you'll see is we've got a number of tables in here. There's a dim date to external that we use to actually import data from Azure into Data Warehouse. We're going to choose the business hierarchies table, but you could use a query. And basically, once we've done that, we'll click on next. Then we choose our destination, which will be Azure Blob Store, and click on next. And the connection name, we'll call it CTO Storage Accounts, and this is from and this is where your notepad becomes useful, because I can take this and put it in here, but I'm pretty sure we can pick it out, to be honest. Yeah, so I was going to all that effort. I didn't need to do it manually at all. So there's the storage account itself. And what you've got is specify a folder that will contain the output files. So we'll browse for that. And there's the data container that we created. So we'll choose that. And we'll choose the compression type that we want. I'm going to put none in this case. Fact. Yeah, we'll put none. And then here's the file format setting. So you're kind of getting the sense here between the connection, we're getting the external data source and the external file format, right? So it's a text format, comma, carriage return line feed. You can use a custom delimiter you want. You can add a header to a file. And then there's advanced settings with regards to escape characters and quote characters. So very much like the external file format settings that you would have. We're going to leave it as this. Click on next. The performance, relay, parallel copy. And as you can see, you can choose the parallelism there. We'll just choose auto. And then we've got the summary. We've got next. It's going to validate the runtime environment. Validation is passed, it's registering the connections within Azure Data Factory, and it's creating the pipeline, and then it's going to provision the activities itself. And now it's provisioning the activities to copy that data across. And what you can do is you can click here to monitor the pipeline. That'll take you to the ADF monitoring screen. But what we'll do is just take a look at the Azure Blob Store within the portal, and we'll do this by going to All Resources, CTO. We'll go to the storage account. We've got the data container here. And as you can see, we've got business hierarchies. If we click on that, we can download that file. And that's the information within the file. So within this, you have seen how you can use the copy activity in Azure Data Factory to export data out of Azure Data Factory into an Azure blob store. Now, a really good use case for this is maybe you've got a view in Azure SQL Data Warehouse that's collecting all the features that you need for a machine learning activity. So then we can query the view, get the information out into a text file, and then we can feed that into machine learning to perform a modeling activity against that. So that's the use case for using this. So let's go back to the slides. You'll be doing a lab on this, so you know. If you ever wanted to attend one of my in-person events or any of my colleagues' in-person events, you can go to learnanalytics.microsoft.com. We have dates on there from our team, but we also have dates on there from really good partners. So shout out loud if you want an in-person event anywhere around the globe. We tend to go to meetings around the globe on this stuff. Anyway, final part, recommendations. So here are some recommendations that we've picked up through being involved with numerous customer engagements. I hope it's loud and clear. Transfer data to blob storage. Now, fundamentally, I suggested that with sys packages. If you've got huge volumes or big volumes of data that you need to put into Azure Data Factory, into Azure SQL Data Warehouse, it's probably better to have the sys package doing all the transformations, creating text files, and having Polybase use the text files as a source for doing it. You might also want to consider splitting those files up. And this goes back to the data warehouse units, where the more data warehouse units you have, the more nodes you have, the more the distributions you spread. Also, if the load user is dedicated to a particular resource class, let's say like large resource class, then you're getting more megabytes per distribution. Now, that means you get more megabytes per distribution, but you get more nodes, distribution spread across the nodes, so more workers. And what workers can do is it can basically take advantage by working on one file at a time. So with DW6000, you get 60 workers. So you could basically split one table into 60 files, so you get one file for each of the readers or workers that are in there. So that's something to bear in mind. And there's a whole host of information on the product groups website. Just do a search in Bing for Azure SQL Data Warehouse. The first non-promoted result that will come back will be to the product group page, and there's loads of techniques that you can do there. So use create table as select data with Polybase for maximum throughput. Always configure a load user and place them in the appropriate resource class, and maximize the number of readers to accelerate the load. So for example, DW1000 Plus has 60 readers, so multiply the number of files by readers for a balanced throughput. So that's what I was referring to a minute ago, and this is useful for the initial load. You would have done, we've done the lab separately here. What I always try and do is do a lab review. Here are the questions that are there. Please feel free to pause now if you want to try and answer those questions yourself. In summary, we've covered a lot. We've looked at the role of the load user and how important it is. We've looked at the different methods for loading data with a single data client and a parallel method. So we saw sys and how that could be used, but really we focused on polybase right from the beginning and how that could be used. Within the polybase demo, we looked at how we can import and export data. I showed you some dynamic management views to monitor your data loads. And finally, we saw how you can use the ADF copy activity to load SQL Data Warehouse. And we finished off with loading recommendations. If you want any more information about the training that we provide, such as online training, videos, instructor-led training, the blogs and so forth, please go to learnanalytics.microsoft.com and hopefully I'll see you at the next video. Goodbye. Looking at Azure SQL Data Warehouse in the context of the Cortana Intelligence Suite. We'll introduce what SQL Data Warehouse is. We'll need to focus on target workload, so what this is for and what it's not for. We'll talk about scaling up versus scaling out and how we can scale the compute in Azure SQL Data Warehouse. And we'll finish off by looking at pause and resume. So, Azure SQL Data Warehouse in the context of the Cortana Intelligence Suite. Firstly, the Cortana Intelligence Suite is a platform and the process to perform advanced analytics from start to finish. So when you talk about the Cortana Intelligence Suite, you'll probably think about the marketing slide that we have with a plethora of technologies, and it can seem quite overwhelming. Well, here in the analytics and data science team, we also think about the process a lot as much as we think about the technologies. But between the team data science process and the Cortana Intelligence Suite, we're enable you to fulfill the platform and the process of advanced analytics from beginning to end. So from a process perspective, we do talk about the team data science process. This starts off with getting a business understanding where you're defining the business objectives. Here you may be identifying data sources. Fundamentally, you're trying to refine the questions that you're actually trying to answer. And once you get through that phase, then you've got the data acquisition and understanding. And this is where you'll use technologies to ingest data, explore data, you might update information about that data itself, and fundamentally you'll want to find places to store it. Modeling deals with the feature selection. Features in this context, it could be a column from a table, it could be an attribute from a cube, it might be a variable within our data set. We're going to wrap these up into the term feature. Essentially, features is data that is of interest to a machine learning model. So fundamentally, there's two really important parts. You've got the model itself that deals with the algorithm, and then you've got the features, which is the data going in. And from this, we create and train the model, we score it, we evaluate it, and if all is well, we can go to deployment and operationalize it. Finally, we've got customer acceptance, where we've got testing and validation. Sometimes the validation may yield results where you have to go back to the process. Maybe the model wasn't right, so you go to modeling and change the algorithm. Maybe the features that you selected were overfitted, so basically it provided a bias in the results, so you might want to change the features, in which case you may go back to the data acquisition phase. The key thing with the team data science process is that it's an iterative process until you get that customer acceptance and handoff. And even then, once that's been accepted, you may come back and review it down the line through retraining and rescoring newer data sets against the models that you have. So we have a platform that can accommodate this process through the Cortana Intelligence platform. A good friend and colleague of mine, Buck Woody, has done a video about an overview of the Cortana Intelligence Suite. I do encourage you to watch that 15-20 minute video. What we're focusing on in the Cortana Intelligence Suite today is SQL Data Warehouse. So this is the first of a series of videos that are going to explore many different aspects of SQL Data Warehouse, but in this video today we're looking at the key concepts that you need to get your head around. So in the context of the marketing slide, the previous slide may have looked like a raft of technologies and oh my god, that's overwhelming. I would ask you to stop and consider this. If you're a SQL Server professional, do you truly know all the technologies in SQL Server as an expert? Reporting services, analysis services, integration services, the database engine, replication, full text search, the full T-SQL language, not forgetting all the other languages across the board ranging from XMLA or DMX or MDX or so forth. I could go on. The reality is that there's very few people who are true experts of the full SQL Server stack, and it's going to be the same with the Cortana Intelligence Suite. You may specialize in an area of the Cortana Intelligence Suite and become a real expert in that area, but essentially be aware of the other areas. So rather than be overwhelmed, I break it down into these 4 parts. On the left hand side, we deal with information management. So we've got Data Factory for the batch movement of time-based data. We've got event hubs that deals with the ingestion of real-time data. So here we can deal with time slicing in real time. And then we've got data catalog that deals with the documentation, tagging of your data sources or data stores. So it doesn't have to be a source, it could be a destination. It could even be an intermediate storage area like an Azure Blob Store. So with information management, you're dealing with that ingestion of data and documentation of data. But at some point you're going to have to store that data somewhere, and this is where we move on to the second phase, which is big data stores. So a lot of people in the BI space will be familiar with a data warehouse, and what these series of videos will do will help you become very familiar with Azure SQL Data Warehouse. So this deals with relational structured data stores. And with Data Lake Store, here we're dealing with unstructured data stores as well. So if you're a BI professional or a SQL Server professional or even a business analytics professional, you know, the first 2 phases of the Cortana Intelligence Suite, information management, big data stores, this deals with what we call in the world of data science features engineering, where you're ingesting that data, you're preparing it, you may do some transformations, you're storing it for downstream analytics purposes. So if you feel that a world of data science is beyond you, it's not, because there's a space in there called features engineering, where a lot of the skills that you have already in the SQL Server space can be easily transferred to information management and big data stores. That's not to say you don't have to learn anything. You do have to learn some new things, but I think the transition into the world of data science will be made much easier by entry points here. But we move on to the analytics phase, where we've got the hot topic machine learning, where you're doing the modeling and retraining models and scoring and evaluating them. We've got data lake analytics that sits over a data lake store using USQL to perform analytics. We've got HD Insight, which is our implementation of the Apache Hadoop standards. You've got to bear in mind with HD Insight, as much as it's a base storage layer with Hadoop, there are also different flavors of HD Insight that you can have, such as Spark, Storm, or HBase. These deals with very specific areas, so Spark allows you to do analytics over huge volumes of data. Storm allows you to do real-time processing of huge volumes of data, and HBase provides NoSQL solutions. And then we've got streaming analytics that's closely tied into event hubs. So with the streaming data coming through an event hub, it's typically sent to streaming analytics to do what we call complex event processing, but we've made this easier by integrating it with the very familiar T-SQL language. The final phase is what I like to call consumption. This is subdivided into 2 areas, visualizations and intelligence. So the visualization, we've got Power BI, which enables you to create your dashboards and reports. Cortana can actually hook into Power BI through the data set, so you can use Q&A through Cortana against Power BI. And then we've got the bot framework to provide interaction points and cognitive services for a raft of APIs that we provide to provide a wide range of detection and so forth in various industries. Today we're going to focus on SQL Data Warehouse, and in this series of videos we break Azure SQL Data Warehouse into a number of different component parts.